Finally, we'll talk about the spin quantum number and spin magnetic quantum numbers S and M sub S. So spin quantum number did not appear in solving Schrödinger's equation for hydrogen atom because the relativistic effects were not taken into account. So it's an additional quantum number that appears in solving the relativistic Dirac equation. So that's the first thing I would like to note about the spin. The spin of an electron is the result of relativistic effects as in Dirac equation. So it appears in relativistic quantum mechanics. The spin quantum number S is equal to 1 over 2. So this is always the case. Then corresponding magnitude of the spin angular momentum vector is square root s plus 1 h bar, which is fixed at square root 3 over 2 h bar. So that's the only possible value we can have. On the other hand, the spin magnetic quantum number M sub S is analogous to M sub L, the magnetic quantum number, in the sense that M sub S can take values between minus S and plus S, so it is either minus 1 over 2 or plus 1 over 2. So it can take two values. Then the corresponding component of spin angular momentum which is along the field axis is S sub z, so I'm assuming the field is in the z direction, is M sub S h bar, which is h plus or minus, well, since I put absolute value here, it's the magnitude is h bar over 2, but S sub z can be plus or minus h bar over 2 in the k hat direction. So we basically see that the magnitude of S sub z, which is h bar over 2, is less than the magnitude of the angular momentum vector, which is square root 3 over 2 h bar. So as expected. Now the spin angular momentum vector also precesses around the field axis on a cone, and you can see that the possible two components along the field axis are plus h bar over 2 minus h bar over 2, corresponding to the two possible values of the spin magnetic quantum number M sub S. So we should note that the spin angular momentum vector precesses in a cone about the field axis, just like in the case of angular momentum. The corresponding magnetic moment, spin magnetic moment, is minus lambda factor g Bohr magneton times the spin magnetic quantum number, where g is approximately 2, the lambda factor. And so we find that with g being 2 and m sub s being 1/2, plus or minus 1/2, the spin magnetic moment along the field direction is always a Bohr magneton. So the spin magnetic moment along the field axis is 1 Bohr magneton. And remember, Bohr magneton was EH bar divided by twice the mass of the electron. We talked about the Bohr magneton in the classical model, where basically I gave also the numerical value 9.27 10 to minus 24 ampere meter square in SI units. So regarding these quantum numbers, the spin, also with the addition of the spin quantum number, we have an important principle, that's the Pauli exclusion principle. And this is about how to place electrons in the orbitals. And Pauli exclusion principle says that no two electrons can have the same set of quantum numbers. So that is to say, two electrons in the same orbital must always have different m sub s values or opposite spins. Okay. The other thing we talked about was about the principal quantum number n and l. When we place these electrons in these shells, the electrons also interact with each other, so that the energy of an electron in general depends on n and l for many electron systems. And if you have a smaller L, the electron is closer to the nucleus, then it's in a more stable orbital, because it sees less of the Coulomb interaction with the nucleus due to the electrons in the upper orbitals will see less of the Coulomb interaction with the nucleus due to shielding of the inner electrons. So if you have a smaller L, the electron is closer to the nucleus, and more stable. If we have a high L and N, electrons in the upper orbitals basically see less of the Coulomb interaction with nucleus due to shielding of inner electrons. The net charge that they see is basically a combination of the inner electrons and the nucleus, so there will be a reduced Coulomb interaction effect on these, and therefore the orbitals become less and less stable as we go into higher orbitals. So that is from 1s to 2p, 2s, 2s, 2p, 3s, 3p, 3d, 4s, etc. Okay, so finally we have finished the discussion on the quantum numbers. The last quantum number we have introduced comes from the relativistic Dirac equation. The quantum number s, spin quantum number s, is always equal to 1/2, and the magnitude of the spin angular momentum is square root ss plus 1 h bar, which is square root 3 over 2 h bar. The component of the spin angular momentum along the field axis can take two values, h bar over 2 or minus h bar over 2. That is the spin magnetic quantum number m sub s. And the spin angular momentum also precesses around the field axis in a cone, and the spin magnetic moment is minus lambda factor Bohr magneton times ms, so it's always equal to 1 Bohr magneton. And we talked about the Pauli exclusion principle. For two electrons, it's not possible to have exactly the same set of quantum numbers. If the two electrons are in the same orbital, they must have opposite spins. The energy for many electron systems is a function of the principal quantum number and the orbital angular momentum quantum number L. If we have a small l, the electron is closer to the nucleus and a more stable orbit. If we have a high L and N, electrons are in the upper orbitals. They see less of the Coulomb interaction with the nucleus due to shielding of electrons in the inner shells. So that makes these stables, that makes these orbitals less stable in that sense.